Okay, any questions about what we have covered until now? We are looking at this projectile motion. We are just imagining that we throw something somewhere in the upward direction, and we are just studying how it moves. So we had already discussed what the how its velocity changes. And we have actually seen that, let's say, initially, we started somewhere here. It will follow such a trajectory. We will study the trajectory now. If this is the initial velocity at this point, the horizontal component of the velocity is still the same. It doesn't change. That is what we had seen. But the vertical component gets smaller. And until at this point, we have the same horizontal component. There is no vertical component of the velocity. And after that point, the horizontal component is still the same. The vertical component starts to grow in the downward direction. So that's what we know about the velocity. Now, it takes, this is at t equal to 0. This is at t equal to tm. Because until tm, it's moving upwards in the minus y direction. After tm, it is moving downward. It's moving in the plus y direction. So this is the point where it reaches the maximum height. Any questions? Now, we had seen that the velocity as a function of time is v0, the initial velocity, plus g of t in the y direction, or let's say a of t, where a is just a constant. This is a constant vector. Now, for such a motion only, the average velocity between two times is equal to the average of the sum of the initial velocity and the final velocity. We average between, let's say, t1 and t2 is equal to v of t1, t2, plus v of t1 divided by 2. This is valid only for constant acceleration. If the motion is not a motion with constant acceleration, this is not valid. So you cannot use this relation. But in this case, this is motion with constant acceleration, so we can use this result. So we can calculate the average velocity from t equal to 0 up to some final time t, and this would be 1 over 2. At the final time, it is v0 plus a of t. At the initial time, it is v0. So this is v0 plus 1 over 2 a times t. The average velocity between time 0 and time t. Well, this is an example where you see the average velocity depends on which time interval you choose. So if it's not from 0 to t, but 0 to 2t, you have a different average velocity. The average velocity changes depending on the time interval that you are studying. We average between 0 to t. So how had we defined it? How did we define the average velocity? It is the velocity is always the displacement per unit time. It's always displacement over time. So if the time interval is long, then we call it an average velocity. If the time interval that we are looking is very short, ideally 0, then it's the instantaneous velocity. So this, the average velocity is average displacement. That is the change in the position of my object divided by the time the change takes place, the length of the time interval. Well, we had already put the initial point, the reference point, initial position we had chosen the coordinate axis such that this was 0. Divided by t. Because this is 0. That is how we had chosen the origin of our coordinate axis. So we know what is the position at the time t. It is t times the average velocity. We had calculated it here. This is equal to v0 of t plus 1 over 2a t squared. Now we can again write it in terms of its components. The x component is I'm already writing the x component only. Let us remember what the x and the y components of the velocity were. So we already know these things. So the x component of the position is the x component of velocity, which is v0 cosine theta, times t. The x component of acceleration is 0. So this is it. It is just motion with constant velocity, the x component. The y component, well, let's see, we have the y component of this one is minus v0 sine theta times t. The y component of acceleration is just g, 1 over 2g t squared. Z component, 0. V0 doesn't have any z component, A doesn't have any z component. And these are the x, y, and z components of our object. The position of our object as a function of time. Now let's see how they look like. Now let's also find the maximum height before studying how it looks like. Now if you remember, we had calculated that the object reaches the maximum height at this time. This is when we reach the maximum height. Until this time, our object moves up. After this time, it starts moving down. So what are the x, y, and z components of the velocity? X at Tm, this is v0 cosine theta, v0 sine theta over g. This is equal to v0 squared over g sine theta cosine theta. Are the units correct? You should always check the units. So the unit of the left-hand side is meters, so the unit of the right-hand side should also be meters. So this is v0 squared, let's see. The unit of v0 squared over g is, v0 is velocity, so it's meters per second squared, divided by acceleration is meters per second squared. Seconds will cancel, and we are left with meters, so it seems to be correct. So this is the x distance So when it reaches the maximum height, this is the distance it covers in the horizontal direction. What about the height? This is minus V0 sine theta, V0 sine theta over G plus 1 over 2 G V0 sine theta over G squared. And if you just calculate it, this is minus 1 over 2G V0 squared sine squared theta. This is the maximum height. Is this the maximum height? Yes or no? What do you mean by height? You don't mean the y component. Okay, you see, when I throw this chalk, what was its maximum height approximately? Let's say 3 meters. Or minus 3 meters. The height is always positive. It's this distance. It's a distance. It's not a component. So the height is the absolute value, but you see V0 squared is always positive, sine squared is always positive. G is just a positive number. So everything here is positive. So the height is just 1 over 2G V0 squared sine squared theta. This is the height. This minus just means that it has moved in the minus y direction, which is the upward direction. Remember, positive y direction is downward. So this minus tells me that it is upward as it should be. So what is the range? So what is the range of the projectile? Okay, so the definition of the range, you should always keep in mind your definition. The range is just the horizontal distance covered. Now, in this case, the only horizontal distance is along our x direction. So the distance covered in the x direction until it hits the ground.
2 times Tn times V0.
Why?
Times cosinus theta.
Why 2 times Tn?
Because it goes up and down.
How do you know that it takes the same amount of time?
It should be. Because
V0 cos theta times t, but what is this t? And your friend is proposing that t is equal to twice Tm.
Yes.
Why?
Because it takes twice to get the maximum height, it takes twice that time to get the bottom.
Why? We are ignoring the air for air.
No, I'm talking about the gravitation.
Okay.
It's constant, so it can't go like blue. It has to.
Why not, let's say, 1.9 times, no, 0.9 times the initial time, or 1.1, it's almost the same. Now, we will see examples where it will be different, by the way. How do you know it's the same? I mean, they are correct. It will take this much time to hit the ground, and when it hits the ground, the vertical velocity will be the same, just in opposite direction, etc. But how can you show it? Okay, that's another. Okay, so I will ask you to calculate the range for this problem. For example, in this problem, the time it takes to go to the maximum height and the time it takes to fall down on the inclined plane will not be equal. Okay, the acceleration is the same. In one of them is pointing up. I mean, the velocity is just changing direction. Acceleration is pointing always in the same direction. It's always the same acceleration, etc. But this will be a completely different problem, and none of these will be correct. How can you calculate the time of flight? From the distance? Well, that's what we are trying to calculate. What is the range? That is the distance that it takes horizontally. How can we calculate it? Well, this will be true because we know that the horizontal motion is motion with constant velocity, and this is our constant velocity. So if we can calculate the time of flight, that is the time it takes to fall down on the ground once we launch it, then we are done. And your friends had correctly said that the time of flight is twice the time it takes to reach the maximum height. At least in this problem it is correct. But how can we show this one? Except then your high school teacher told you that it is twice. How can you verify that he is true?
I think it's twice because it stops at the height where it starts.
Okay. Well, I mean, as a comparison, I'm just proposing this problem. I mean, I should be doing something different in this problem because the range in this problem will be different. But what you say is when it reaches the maximum height, it will stop. Well, it is the same thing over here. So why is this problem different than the other problem? How can we take that into account? Why? Again, what difference this problem would make in your answer?
If we could find the height at which it touches the slope, we can put that into our calculation and find the time. And using the time, we can find out exactly how long it took for it to reach that particular height.
Okay, in this problem, the time, and in the previous problem, the time will be exactly the same, because you see, until it hits this point, this motion doesn't care whether this inclined plane exists or not. So there won't be any change until this height. But of course, this time, the time it will take to hit this point will be different than in the previous problem. How can we determine this time of flight? Okay, how do we calculate that time?
We have the maximum height, we have the velocity at the maximum point is 0.
Okay, so that we know the time it reaches the maximum point. How can we calculate the remaining time? Using which one? This one? No, the previous one. Okay, we had calculated the velocities, and from this information, how can we obtain the time it takes to fall from this height to the ground back again? We can? Okay, so how can we? I should say that minus V0 sine theta plus g time of flight, let's say, is equal to what? This is the y component. Is this one as a function of time? Okay, how do I make
Substitute 0 to r.
0 to r? Well, I cannot substitute 0 to r because it will never be back to the 0 point. But you have I mean, the y component will be 0. That is what we mean by it hits the ground. That is the mathematical expression for hitting the ground. The y component is 0. Which other function?
You can write a function about the speed on y component, so you can calculate how much time it takes to fall.
What is that function?
Our initial velocity is 0, our acceleration is 9.8.
G.
So if we integrate g 2 times with respect to time, we can get the height.
No, you see, we have already we don't need to integrate. If you want to calculate the position as a function of time, we already know the position as a function of time. This is the position as a function of time. We already have done that. And we can just use this relation. So it's, again, back to if you just look at the question, what does the question ask? It's asking you, when does it hit the ground? What is the mathematical expression for hitting the ground? It is just y of t, y of tf. This should be equal to 0. This is the definition. And this would tell me what the time of flight is. We already know what y of t is as a function of time. It is minus v0 sine theta tf plus 1 over 2 g tf. This should be equal to 0, tf squared. Well, this equation has two solutions. Tf is equal to 0, and Tf is equal to twice V0 sine theta over G, which is nothing but twice Tm. Well, this is not what we are interested in because we already know that at t equal to 0, our object was on the ground. So at t equal to 0, y of t was also 0 because it was the beginning of motion. That's not the time of flight. So this is not the solution we want. This is the time of flight, and as you have pointed out, it is twice the maximum height. So as most of you had said, the motion is quite symmetrical, so the acceleration is constant. The trajectory is also will be symmetrical. The ground is symmetrical around the vertical. So the time it will take to go upward will be equal to the time it will take to go downward. But if you go back to, if you look at this problem, you cannot apply the same principle because this inclined plane is not symmetrical about the vertical. So it will not be twice the time it will take to reach the maximum height. Now, we will look at this problem next, but for the time being, let's just stick with this one. So if your question is about this one, yes. Okay. Time of flight. Okay. Now, without making further assumptions, like the symmetry of the motion, like that the final vertical velocity, the vertical component of the velocity should be equal to the initial vertical component of the velocity in magnitude but opposite in direction. These are the additional assumptions you make. Without making these assumptions, this is probably the only way you can obtain the time of flight. And once you know this result, then you can, of course, say that, okay, the velocity components in the vertical direction will have the same magnitude, just pointing in the opposite direction. It takes twice as much to fall on the ground as it takes to reach the maximum height, etc. So we know the time of flight, and we can calculate the range. Range will be V0 cosine theta. Now, range, let's say, it's nothing but x at Tf. It will be V0 cosine theta plus times twice V0 sine theta over G, and this will be V0 squared sine 2 theta divided by G. This is the range of my object. So what can we say about this range expression? So this is the range. Let's say that this is 30 degrees or pi over 6. This is also pi over 6. One is 30 degrees, the other one is 60 degrees. They have the same initial velocity, initial speed. What can you say about the ranges? They will be the same. Because you see, one of them is sine of 2 pi over 6 or pi over 3. The other one is sine of 2 pi over 3. And since they are equal, these two objects will have the same range. Will they have the same time of flight? Which one will have this shorter time of flight? Okay, the one aimed downward. This one will have a smaller time of flight. This one will have a larger time of flight. So if the time of flights are different, how come they have the same range? Their speeds are the same. X components are different. So as theta gets smaller, okay, the time of flight gets smaller, but the x component of the velocity gets larger. As theta gets larger from 45 degrees or pi over 4, okay, the time of flight gets larger and larger, but the x component gets smaller. So for these two angles, they just compensate. So the smaller one will have such a trajectory. The other one will have such a trajectory. Now, they are supposed to be parabolas. They are supposed to be symmetric, let's say, but they will have the same range. Now, what is the shape of the trajectory? How can we determine the shape? Not the time. I don't want to know the position at every time, but let's say if you tell me the x point, how can be the x component of its position? How can I tell the y component of the position? So these are the positions as a function of time. What I want to find is y as a function of x. You tell me what the x component of the position is, I will tell you what the y component is. The first one. So if I know x, the first one tells me what t is. So t will be equal to x over v0 cosine theta. And once I know t, I can determine what y is. Y will be equal to minus v0 sine theta, x over v0 cosine theta, plus 1 over 2 g t squared is x squared divided by v0 squared cosine squared theta. Well, basically, y is minus ax plus bx squared. with some constants A and B that depends on the angle theta and the V0. So do you recognize this mathematical shape? It's just a parabola. So if this is the y, this is the x, so does this parabola look upward or downward? Well, I can always draw the graph whichever way I like. So it's an upward-looking graph. Of course, you see, Earth is over here. It's not over here, it's over here. This is upward, this is downward. Now, any questions on this one? Do you know what a curved ball is? No, it's not the shape of the ball itself, but you have probably, if you have ever watched a football game, especially in the corner shots, this is the goal, this is the corner, you hit the ball, and the ball, according to our derivation now, the ball should move in this plane. This is the y-axis, this will be the x-axis, or this is the y-axis. There is never a z component of the ball, the motion of the projectile. But in the actual game, the ball just starts moving, it moves in this plane, and then it falls somewhere over here. Definitely not in that direction. So what is wrong? You see, in our derivation, it is not possible to have a curved ball. So z of t is equal to 0. Always. So what did we miss? We didn't?
Maybe there's a wind.
Even if there's no wind, assume there's no wind, even in the football game, the ball will still move in that direction. So, okay, in this problem, we could have assumed that the ball is still rotating and it will not curve. Nothing will change in this derivation.
Counted as we hit the center of the object?
No. In this one, I just assume that it has an initial velocity. That's the only thing I assume. I mean, whether you hit the center or the side or whether it is rotating or not, there is nothing in this derivation would have changed, except that we ignored one thing. The ball itself is? In this derivation, where did we assume that the ball is spinning? Is not spinning, or let's say. Okay, but I mean, which part of this derivation would you change if you want to take that into account? There is one thing we ignored in the derivation at a given step. You should be aware of your assumptions. That will be the point. What are the assumptions that we made? So that, I mean, if you are not careful about the assumptions, the moment you observe the curved ball, you can say that, okay, all of this is bullshit. It doesn't work. It's not correct. But that's not true, because this derivation is based on certain assumptions that we had made implicitly. And only under those assumptions, this derivation would be correct. Which assumption doesn't hold in the case of a curved ball? No. Air. Not the air friction, but air itself. It's not about the friction. We ignore the air. In a place where there is no air, even if the ball is spinning, it will follow these equations. This will still be satisfied. Even if whether the ball is spinning or not, whether you hit the center or the side, it will not make any change. The ball will not curve. only if there's air plus the spinning motion. Both of them together will cause the ball to curve. Now, how does it cause the ball to curve? We will study at the end of the semester, not now. So that is one of the assumptions we made. There's no air. Only under that assumption, or in cases where that assumption can be approximately true, for example, if I take a small object, small massive object, if I throw it, that's a good assumption that there's no air. But if you take a piece of paper and if you just throw it, well, that is definitely not a parabola. Now, we will study the friction forces and rotation later on, and we can discuss what's happening in these cases. Now, before you go, let us look at this problem. We don't have time to solve it, but we can discuss how we can proceed. Let's call this angle theta. This angle is phi. It has an initial velocity. Let's call it v0. Okay, where should we put the reference point? At the starting point, okay. So, which would be the x, y, and z directions? Well, we already know that the trajectory will be a two-dimensional motion. It won't really be a three-dimensional motion, so it will always move in a plane. So let's only fix the x and the y coordinates. X is horizontal. Y is the vertical. Okay, this is one choice. Well, you can just repeat what we had done for the ordinary projectile motion. And these expressions are in fact still valid. Because you see, okay, these are the same, we use the same set of coordinates. The y, well, the only change we will have is that now the y is in the upward direction, not the downward direction. So we have to change the sign of the y. So I don't need to resolve this problem because this is almost the same as the previous coordinate axis that I had chosen. And then another change is the theta. Remember how we defined the theta. In this case, theta, in the previous case, theta was the angle that the initial velocity makes with the horizontal. Now in this problem, the angle that initial velocity makes with the horizontal is theta plus phi. That is how we defined it. So this is the solution of the position of the object as a function of time. Now, how can we determine the time of flight? So because if we want to determine this point over here, we have to know how long it flies. And once we know how long it flies, then we can determine the x and the y, and so we can determine this distance. So in this problem, how can we determine the time of flight? This one. Okay, so. Okay, so you are saying that y of t is equal to 0? You mean move over here? Well, you see, of course you can move it, but we don't know where this point is yet. And I wouldn't advise you to move your reference points once you fix it. Don't play with your reference points. Fix it once and let it stay there.
Time before
It won't be the same. Not in this case. You see, what does it mean to be on the plane? And before we were thinking about, we had this horizontal ground, and then we determined the time of flight from the question itself. What does it mean to be on the ground? And we said that to be on the ground means y is equal to 0. So in this case, what does it mean to be on this inclined plane? Just fix any point, not necessarily this point. How can you determine whether that point is on the plane or not?
Let's give the range of the motion t that are coordinate on y-axis has to be t times tangent of theta.
Yeah, more, you see, this distance over here is nothing but y of t. TF, let's call it, time of flight. This distance is x of t of flight. And here we have this nice right triangle. Y of t of flight divided by x of t of flight should be equal to tangent theta. If you have any points on this plane, on this line, its y coordinate divided by its x coordinate should be equal to tangent of theta. This is just a mathematical expression for a point being on the inclined plane. And we know y of t, we know x of t. Well, theta is a given in the problem, so you can just solve this equation for the time of flight. And once you know the time of flight, you can determine y, you can determine x, and you cannot. Now, any questions on this one? Okay, that was kind of the boring solution. We only use the result we had from the previous problem. Now, that's valid, it will give you the correct solution, but let's choose a different coordinate axis. I mean, you see, in general, in real life, you rarely get a preferred coordinate axis, the problems get complicated. But in example questions, you will always have some preferred axes, like the direction of the acceleration. If you choose one of your axes in the direction of the acceleration, which is pointing downward, or in the opposite direction, this is A. Some of the components will become 0. At least the components of the acceleration will be 0, so your question gets simple. But there is an alternative. You can also choose this one. Let's say this is the x, this is the y. Now, in this one, the acceleration had a simple form, and we even had our results from the previous example. So we could just, but the condition for being on the plane was kind of complicated. So how do you determine a point is on the plane? It should satisfy this relation. Now with this new coordinate axis, now the acceleration will have both x and the y components. So you have to take both into account. So the acceleration will have some x component and some y component. And of course you have to go and solve for x of t and y of t. So how do you determine the time of flight in this case? What is the condition that would allow you to determine the time of flight? Well, that is basically the same question as how can you test that a point is on the plane, on the inclined plane? What is the condition that the coordinates of a point should satisfy if it lies on this inclined plane? Okay. True. In this case, y of tf is equal to 0. Because this is our origin, this is our x-axis, this is our y-axis. So if you are on the inclined plane coincides with the x-axis. So if you are on the inclined plane, you are on the x-axis, but any point on the x-axis has y equal to 0. So if the trajectory, if your object is back on the inclined plane, then the y should be 0. Just like in the case of the horizontal case. Because in the horizontal, if we choose the x-axis to be parallel to the ground, that's horizontal, then the y component when we are on the ground is 0. It's exactly the same. The difference, the price you pay for this simplification, let's say, is that acceleration is now a more complicated object. And how can you determine if you are using these coordinate axes, how can you determine the height from the ground? It's no longer the y. Which plane? No, the height is always, I mean, you see, when I ask you the height, you don't ask me the height from the plane, you height from the ground. How can you determine the height? Well, okay, I will stop it over here. This will be your homework. You will have one homework today for next Tuesday. It will be the simpler one. You will have another homework on Thursday for the next Thursday. Now, any questions about the material we had covered? Yes. Now the y component will change. You see, as the object is moving, the y component increases and then it decreases. Now when it hits the plane, the y component is again 0. Just like when you throw an object vertically up, not vertically, in a projectile motion, it first increases, the height increases and then decreases, and eventually it hits the ground. No displacement in the vertical direction. In this case, the object shouldn't be displaced in the y direction. Net displacement though. Other questions? It will be in auto class. So all the homework will go in auto class. Okay, see you on Thursday.